Chemistry, we're on to our final lesson in the equilibrium unit, and this is on Le Chatelier's principle. So the reaction quotient is computed the same way as an equilibrium constant K, except Q is computed using the existing non-equilibrium concentrations in a reaction. So in other words, it can be computed with any concentrations of products and reactants, whereas K is computed specifically with equilibrium concentrations. The reaction quotient is used to tell which way the reaction will flow. If Q is equal to K, the equilibrium constant for a particular reaction, then the reaction is at equilibrium. If Q is less than K, the reaction has excess reactants. That means the denominator in the law of mass action is too big, and so there are excess reactants, so that means it will move in the direction to produce more products and have fewer reactants. So it's said to favor products, so get used to that term. It's just the term used in chemistry. Favoring products means the reaction wants to move toward creating more products. If Q is greater than K, then that means the numerator of the law of mass action is too big and the reaction has excess products and will move backwards. It will move in the reverse direction from right to left to create more reactants. And that situation is said to favor reactants. So the reaction from the previous example in the earlier lesson looks like this. We've seen this equation before. So let's just make up some concentrations of reactants. So let's say that H2 is 0.065, both of those times 10 to the negative third. So these reactant values are the same as in the previous example in the earlier lesson. You don't have to remember that example. But this product concentration is larger than the previous equilibrium value in that previous example, so we should expect the reaction to flow from products back to reactants in the reverse direction. In other words, this was a larger value of concentration of product than we had before. So compute Q the same way as Kc, so this is how you would do it. You'd put products on top and raise them to the power of the coefficient. So 2hi means the 2 in front of hi would become the exponent, and then you plug in the number that we have down there for the concentration of hi. On the bottom in the denominator, you have the 0.065 times 10 to the negative third and the 1.165 times 10 to the negative third. Those both have exponents of 1. And if you did that, you'd find Q is 90. In the previous example, it was 50. Since Q is greater than Kc, it was 50, actually 51 from the previous example, the reaction will move in the reverse direction and reduce the products and create more reactants. So Le Chatelier's principle states that if a chemical system at equilibrium is disturbed by a change in temperature, pressure, or concentration of one of the components, either reactants or products, or the temperature, pressure, then the system will shift its equilibrium so that it counteracts the effects of that disturbance. Sometimes books refer to that as putting a stress on the system. If the reaction changes so that it favors products, so that more products are formed, it is said to favor products. If the reaction changes so that more reactants are formed, it is said to favor reactants. So here's an example. So the reaction below is initially at equilibrium. If reactants are added or products are removed, the reaction will move toward the products. That's to say a change in concentration. So if you add H2 or I2, you don't have to add both, just add one of them, or on the right side you remove some HI, that would cause this reaction to move to the right and favor products. Think of this think of the reactants and products like rooms of people. And if you put more people on the left side, they're going to want to get more comfortable because it's too crowded all of a sudden. So now they're going to move over to the right side. They're going to move over to the room on the right. If, on the other hand, you had a certain equilibrium between the two rooms where everybody was happy, now all of a sudden you take products out, you remove HI, then that makes that room less crowded. The people over on the left see that there's more room over on the right. They can be more comfortable and have more space, and so they'll move over to the right. So either adding to the left side or removing from the right side will cause the reaction to move to the right to favor products. If reactants are removed or products are added, then it's just the opposite. The reaction will move toward reactants. That's a change in concentration. So if you either remove H2 or I2, or you add HI over there on the right, that favors reactants. Again, if you add more HI, then that room becomes crowded over on the right, and people want to be comfortable and have their space, so they're going to move over to the left. Or if you take some of the people out of the room on the left, that's the H2 and the I2, the people over on the right will also see that they can be more comfortable and have more space over there, so they will move over to the left. So simply think of the crowded room when you're dealing with concentrations. Okay, so we're using the same principle here. Now we're going to deal with heat. In endothermic reactions, heat is treated as a reactant. In other words, an endothermic reaction is one that naturally takes in heat, so it can move from left, that would be H2I2, over to the right, that's the HI. So that reaction, if it's endothermic, naturally wants to take in heat. So you treat heat as though it's a reactant. So heat added pushes the reaction to favor products. So it's going to go in that direction. So again, endothermic reactions naturally take in heat. If you give them heat, if you feed them the heat, then they are going to move from left to right. So that's true of any endothermic reaction. So that's going to favor products. In endothermic reaction, heat is treated as a reactant. So heat removed pushes the reaction to favor reactants. So now all of a sudden you're starving it, you're depriving it of heat, a reaction that naturally would want to have heat come into it on the reactant side. So if you take heat out, then the reaction is going to move backwards. It's going to move in reverse from HI over to H2 and I2 in this direction. So that's going to favor reactants. So think about that one again. This reaction, if it's endothermic, naturally wants to take in heat. It's a positive delta H. But now you're removing heat. You're doing what it doesn't like. You're taking away one of the things that causes it to move from left to right. Therefore, it's going to move in the other direction from right to left. Now, if it's an exothermic reaction, it naturally wants to give off heat. That's a negative delta H. So heat is treated as a product. It comes out on the right side, and it's given off to the atmosphere. So heat removed pushes the reaction to favor products. So why does that happen? The way I think of it is, it's just you want to think of these little metaphors. Heat wants to come out of that reaction. That means the room is going to get hotter and hotter. So all of a sudden, what you'd call the surroundings are suddenly being filled up with more and more and more heat. If you can take that heat out, in other words, you cool off the reaction, then it will be easier for heat to get out into the surroundings. So if you can remove heat from a reaction that wants to give off heat, then it's going to favor the products. It's going to want to move to the right. In an exothermic reactions, heat is treated as a product. If heat is added, heat added makes it more difficult for heat to exit and pushes the reaction back in favor of reactants. So again, heat is trying to get out. It's trying to escape an exothermic reaction, but you keep somehow shoving heat in. The way you would do that is by turning up the temperature of the reaction vessel or of the surroundings. You'd be shoving heat into a reaction that wants to be able to give it off. So you're kind of preventing that reaction from giving off the heat it wants to give off. So adding heat is going to push the reaction backwards. It's going to push the reaction back to the left. So think about that one a little. It might not be quite as obvious. Okay, now we're going to take the example of pressure increases by changing the volume. Now this would apply to gases only, not molar solutions. So let's take this reaction. We have 1 mole of N2O4 and it's going to decompose into 2 moles of NO2. So the reaction below has 1 mole on the reactant side and 2 moles on the product side. If pressure is increased, the reaction will try to return to equilibrium pressure by reducing the number of moles, which will reduce the pressure. So stop and think about that one. If you go back to PV nRT and you increase the number of moles on the right side of PV equals nRT, N is the number of moles, that's going to increase the pressure. So let's do it in the reverse direction here. Let's say you increase the pressure first on the reaction. It's in its happy place, it's at equilibrium, suddenly you turn up the pressure. How could you do that? By squeezing down the volume. So you squeeze down the volume, the pressure's gone up. So if the pressure is increased, the reaction will try to return to equilibrium by reducing the number of moles, which will reduce the pressure. So it's going to want to go from the side that has more moles, in this example it would be the right side, back to the side that has fewer moles, that would be the left side, the 1N2O4. So by increasing the pressure, the reaction says, hey, it's too much pressure, it's too crowded in here. I want to have fewer molecules in this container because the pressure has gone up. And so what it's going to do is take the 2 moles of NO2 and convert them back into 1 mole of N2O4. Not all the way, but until it gets back to an equilibrium situation. So this can be done by turning products back into reactants in the reaction above. So when you increase the pressure, it's going to favor the side with fewer moles. Again, more pressure means the molecules feel too crowded. They want to have fewer molecules in order to get the pressure back to normal again. So it's going to go from the side that has the more moles, the 2 NO2, to the side on the left, which has fewer moles, 1 N2O4. Now, if pressure is decreased, the reaction will try to return to equilibrium by increasing the number of moles. That will increase the pressure. So in other words, you cause the pressure to decrease. It says, I'm not happy with this lower pressure. I want to get back to a higher pressure. How can it do that? By increasing the number of moles in the container. That will increase the pressure back to equilibrium. So this can be done by turning reactants into products. That's 1 mole to 2 moles in the reaction above. So just remember PV equals nRT. Increased pressure increases the side with fewer moles, and decreasing the pressure is going to increase the side with more moles. Now we're going to talk about a concept called solubility product. So we have used solubility rules for ionic compounds in water. We determined that a compound was either soluble or insoluble. So for example, we said that calcium carbonate, look down on the bottom right, with CO3 2-. If you added a calcium Ca2+ to that, that would make calcium carbonate. That's what eggshells and seashells are made of, and that would be insoluble. Well, in the real world, nothing is 100% insoluble. Little bits of it will dissolve in water, even of eggshells or seashells, but very, very small amounts. So many of the ionic compounds we classify as insoluble don't dissolve, actually do dissolve in small amounts. This means the solution contains some of the dissolved ions, but mostly the undissolved compound. It mostly does remain undissolved. This produces an equilibrium situation with its own equilibrium constant called solubility product. And all equilibrium constants have some kind of subscript, and this one is Ksp, K sub Sp, standing for solubility product. So at equilibrium, we're going to look at an insoluble compound. If you looked at our solubility rules, AgCl, silver chloride, would be insoluble. So at equilibrium, an insoluble solid is mostly undissolved compound and a small, very, very small amount of dissolved ions. So a very small amount will dissolve into a silver cation and a chloride anion. The law of mass action for the solubility product reaction below is, you see it, and there you see, the Ksp is going to equal the products only. The concentration of silver ions times the concentration of chloride ions raised to the first power because their coefficients are 1. You do not include the AgCl because remember one of our rules was if it's a pure solid, and in this case AgCl is a solid, not a pure solid, but AgCl is a solid, then it will not be included in the law of mass action. So you only include the products in this case. Solids are never included in a law of mass action, so only the product side is included. So example, write the solubility reaction and the law of mass action for the following. So you should know how to write this reaction. This is an ionic bond. It's 1 magnesium and 2 chloride ions. 1 magnesium ion and 2 chloride ions. So that's the way you would write it. So remember, that's not a Cl2 molecule. Those are 2 chloride ions in solution that break apart from each other, not only from the magnesium, but from each other. So you end up with 3 particles there. So the 2 chlorides break into separate ions. There are 3 ions produced by this reaction. So the law of mass action is, as you see below, it's the Ksp equals the magnesium. Now don't worry about the ions. They have nothing to do, the 2 plus and the minus. The magnesium 2 plus is raised to the first power, and the chloride ion, there's 2 of them in the reaction, so you have that as an exponent, Cl minus to the second power. The coefficients become exponents in the law of mass action. So now we're going to introduce a concept called molar solubility. So molar solubility is the number of moles of undissolved ionic compound, that would be the solid, in 1 liter of solution. So a saturated solution is a solution that has reached the limit of its ability to dissolve any more of a solid. Any additional solid added will sink to the bottom. So it's going to be, the molar solubility occurs when you've reached that limit of the ability of the solution to dissolve. So we can start with the Ksp, the solubility product of the compound, figure out the concentration of cations and anions, that would be using a Rice table, and then from that figure out the molar solubility of the compound. Or we can go in the other direction, and we'll see examples of both of these. We can start with the molar solubility of a compound and go backwards, go to concentration of cations and anions, and then go back and figure out the Ksp. So this is a standard Rice table operation. We'll show you how to do both of those. So we will learn how to convert between solubility product, concentrations of ions, and molar solubility. Okay, now we're given a problem. The solubility product Ksp value for PbCl2 is 2.4 times 10 to the negative 4th. And you notice that PbCl2, if you go to your solubility rules, you would determine that that's insoluble. What is the molar solubility of 0.2 molar PbCl2? So we're going to say a little tiny bit of this PbCl2 is actually going to dissolve. So there's the reaction. Convince yourself that that's correct. It's going to break off into 1 Pb ion and 2 Cl minus ions. Okay, the Cl2 is not a molecule of chloride, it's 2 ions breaking off. All right, so let's go ahead and fill in the equilibrium table and write the law of mass action. So we're starting off with 0.2 molar of PbCl2, and our change, we're going to have 0 molar of Pb and 0 molar of the Cl over on the right because we weren't given any concentrations, so we assume that there's 0. Now the change in the PbCl2 column is minus S. The variable S is used in solubility product problems because it represents the molar solubility. You could have used an X just like we did before, but generally books use an S for this. So now what we're going to get in the equilibrium line is 0.2 minus S. Now over under Pb2 plus, and again the ion, the 2 plus has nothing to do with this, it's just lead, Pb. You're going to add an S there because the coefficient is 1. So that's going to give you S in the equilibrium line. The coefficient in front of Cl is 2, so you're going to add 2S there. Again, S is the same as X has been in previous problems. And so that's going to give you 2S down there. Now you write the law of mass action, and there it is. Ksp equals Pb times Cl raised to the second power. You do not include the PbCl2 because it is a solid. So all you have are the products up on the top. And now that's going to give you, if you plug in the number for Ksp, 2.4 times 10 to the negative fourth, and you plug in the algebraic expressions for Pb and Cl, you have an S down in the bottom equilibrium line and a 2S down on the bottom for Cl on the equilibrium line. And now you put in the 2S and you also square it because that's what the equation, the law of mass action, says to do. So that's going to give you 2.4 times 10 to the negative fourth equals 4s to the third. S times s squared is s to the third. And solving for s, so you divide by 4, and then you've got to take the cubed root of, and I'll show you how to do that on the calculator, you get s equals 3.9 times 10 to the minus 2. This is the molar solubility. So the s value is the molar solubility of PbCl2. Fraction, the molar solubility for MnCO3 is 4.2 times 10 to the negative 6. So now you're given a molar solubility. What is the Ksp of MnCO3? So there's the reaction. Convince yourself it's correct. You're going to end up with one manganese ion and one carbonate ion for the little bit that does dissolve. So we're going to start off with 0.3 there, and 0 under manganese on the product side, and 0 under carbonate. Now we're going to go down in the manganese column. The molar solubility is always that number. It's the S number. So it's the number that would go in that slot right there. You put the negative sign on it because it's decreasing in concentration. Okay, so the molar solubility number, 4.2 times 10 to the negative 6, is the number that goes underneath the solid that we're dissolving. The negative sign is because it's decreasing. So that's always going to be your molar solubility right there. And now if you subtract the change line from the initial line, you're going to end up with that number on the bottom. But that number is completely irrelevant because it's a solid MnCO3, so it doesn't go in the law of mass action. Now over on the product side, you're going to end up with positive 4.2 times 10 to the negative 6th. The coefficient is 1 in front of Mn, so that's going to be 1. And then that's going to give you the change. You're going to have 4.2 times 10 to the negative 6th at equilibrium. Same for carbonate. You're going to add that same number and get that same number there. So the only two numbers we're interested in are on the product side down in the equilibrium line. So there's the law of mass action. Okay, there's no exponents because both coefficients are 1. So you're simply going to multiply 4.2 times 10 to the negative 6 times 4.2 times 10 to the negative 6th. And you end up with the Ksp of 1.8 times 10 to the negative 11th. So note that the very small value for Ksp means that this is highly insoluble. Okay, so that takes care of our lesson on Le Chatelier's principle and on solubility product.